this video, I'd like to talk about the singular value decomposition as a method for pattern recognition or pattern extraction. Suppose that you performed some experiment and got the following result. The first experiment result was 1 and 2. The second one was 1.1 and 2. The third was 1 and 2.1, and maybe the fourth experiment turned out to be 0.9 and 1.9. So you have 4 results for 4 experiments. If you draw those results, you'll find out that this might be the first one, 1 and 2, so this might be the first point, 1 and 2. The second point will be 1.1 and 2, so this might be the second point. The third point is 1 and 2.1, so this is the third point. The fourth point was 0.9 and 1.9, so this was somewhere here, just like that. So every one of those can be thought of as a vector. So this might be one vector, this might be another vector, and a third vector, and here finally a fourth vector to this point. And your target right now is try to extract the underlying pattern in all your data points resulting from your experiment. You see that all of those points are very similar or very close to each other. And you might want to get one vector representing all of those data points. You can have many methods to perform this, but one of those methods is the SVD. Remember that the SVD allows you to decompose a matrix A into a summation of rank 1 matrices. In this case, since the rank of the matrix A is 2, then we can have A to be equal to sigma 1 A1 plus sigma 2 A2, where A1 is equal to U1 V1 transpose and A2 is equal to U2 V2 transpose. Now you might ask yourself the following question. Could I get a rank 1 matrix that is as close as possible to this matrix? A rank 1 matrix where the error between the rank 1 matrix and the original matrix is very small? The answer is yes. If you choose some matrix B, for example, such that B is equal to, let's say, 1, 2, 1, 2, 1, 2, and 1, 2, then the error between this matrix B and this original matrix right here will be very small. Actually, you can think of the original matrix A as a summation of 2 matrices. One of them might be 1, 1, 1, 1, 2, 2, 2, 2, and the second one might be, I might have here 0, 0. Here I might have 0.1 and 0. Here I might have 0 and 0.1. And here I will have negative 0.1 and also negative 0.1. So the original matrix A can be decomposed into this form. Now this is a rank 1 matrix while this is a rank 2 matrix, so this is not a valid singular value decomposition, but you might expect that a valid singular value decomposition will tweak those values a little bit until this also becomes a rank 1 matrix and this remains a rank 1 matrix, and this matrix will be very similar to the original matrix. What I want to say is that this matrix right here could be able to be decomposed into the summation of 2 matrices. One of those matrices can be very closely similar to this original matrix, and this other matrix will have only the fine-tuning details that make these vectors different from each other, those very slight differences between the vectors. Now, assuming that this right here will be the first matrix and this right here will be the second matrix, and knowing the information that U1 V1 transpose will have very small values inside the matrix itself, then in order to have this first expression very similar to this matrix right here, we need sigma 1 to be slightly large because the values right here are slightly large. So we need sigma 1, the weight or the importance of the first matrix, to be considerably larger than this sigma 2 because this matrix right here has less importance than this matrix right here. Again, that's because sigma 2 A2 will have small numbers while sigma 1 A1 will have considerably larger numbers, and again this is not the correct singular value decomposition, since if it were the correct singular value decomposition, then this matrix right here would have been a full rank, but actually, as we will see soon, the correct singular value decomposition will be very similar to those two matrices right here. So we expect the following. We expect if we get the SVD of this matrix that sigma 1 will be considerably larger than sigma 2. Also, we expect the columns of this first matrix A of sigma 1, A1 to be very close to the columns of this matrix right here. But we also expect them to be direct multiples of each other, since this matrix will be a rank 1 matrix. Another thing we will expect is that the first singular vector u right here, the first left singular vector u, will be somehow very close in direction to those columns right here, because the rank 1 matrix sigma 1 A1 will have columns that are multiples of u1 and rows that are multiples of v1 transpose. So we expect u1 to have components very similar to those, except it will be a unit vector. So the components of u1 will be very similar to, let's say, 1 over root 5 and 2 over root 5. And also the components for v1 transpose will be very similar to, let's say, 1 over the magnitude. So this will be 1 over root 4, I think. 1 over root 4 and 1 over root 4 and 1 over root 4. So this is what we expect, and we will go to MATLAB and get the correct actual singular value decomposition of such a matrix. Here I wrote this code. In this code I have this same matrix A. Then I am getting the singular value decomposition, getting the first left singular vector and the first right singular vector, and also getting the first singular value, and then constructing this A dash, which is equal to sigma 1 u1 v1 transpose. So let's see the result. Let's run this and go to our console, and in our console we see the following. This is the original matrix A. This is the matrix A dash, the first rank 1 approximation of the original matrix A. And as you can see, the values here are very close to the values here. This is 1, this is 1.0006, and this is 2, this is 1.9997, and so on. Of course, the rank of A dash is equal to 1, as it must be. And so all the columns are multiples of each other, and also all the rows are multiples of each other. Now let's look at the matrix U. Here I have this first vector U, and as you can see, the second component is somehow twice the first component. Of course, we have this negative sign right here because the singular value decomposition here expected that the direction we are looking for is actually this direction. As I said before, the singular value decomposition have some ambiguity regarding the sign, and since MATLAB doesn't know what we are really trying to do with those numbers, it doesn't know that those are some data points, it only got one of the valid left singular vectors. But if we know what we want to do, then we would choose the vector in the opposite direction, the negative of this, to represent our data, because we know what we are doing, while MATLAB doesn't know, and so it only deals with the problem as a purely mathematical problem with no intuition at all. Also, if we look at the V, we will see that the V1 transpose is very close to every rows of those matrices, or the components of V1 transpose are very highly related to the components of the rows of this original matrix here. So here V1 transpose is actually this first column. This is V itself, so V transpose. The first row right here has components slightly in the range of 1, 1, 1, 1, just as the original matrix right here has components in the range of 1, 1, 1, 1. Now, if we look at the singular values, we will find out that the first singular value is equal to, here, I think here, the first singular value is equal to this value, and the second singular value is much smaller than the first singular value, just as we expected. So by this very simple example, we have seen how the SVD could extract the features or the patterns hidden in our data points. In the next video, we will cover another example for pattern extraction using singular value decomposition.